couple of things which are interesting for me. First of all, I found your circuit, which amplifies the signal, what you get from the organic stuff, which doesn't need to be organic stuff. Actually, it could be connecting to the human body, and I guess it measures when your blood pressure or something like that. It is used for cardiogram, right?
So small changes in like electric signals on the skin, which would relate to your heartbeat, would be picked up.
Right.
So here we're looking at like tiny changes in electrical activity within the mycelium, within the moss.
Yeah, right. So for me it was very interesting that you could kind of interconnect like nature and computer first of all. And the circuit is very easy. You know, what you buy in the shop, the sensors pretty much made, which clean up maybe noises and other stuff. But I think your sensor is pretty straightforward going, and it's very easy to assemble, and it's very easy to get something into computer and back. So I was thinking of it and wanted to start playing with feedback loops, maybe interacting to what is the mushroom, let's say in this case, giving to the computer what is picked as a signal. So if you have this kind of feedback loop, so you can maybe you can follow up the evolutionary process, how things could change within the time. Because feedback loops, when they come up through electric current passed through, so maybe some signal from outside would be picked and then it could be sent again through the current. And I think in the evolutionary terms it could come up to very interesting formats and maybe designs. I don't know. It depends what you think of. Sound, for example, right? So the sound could evolutionarily continue being generated, let's say. So that was my thought, what I was thinking. And of course,
I think it's interesting to see how like the mushroom could maybe change its growth pattern over time with this feedback loop, so it's kind of like setting something in motion which is not happening before. As soon as you kind of introduce this apparatus, that you're kind of pulling those two things, like the technology and the mushrooms, kind of closer together, like they're starting to have kind of influences one on the other, changing growth, changing our experience of them. So this idea that these technologies allow some kind of different connection between ourselves and this other very foreign species, the mushroom or the mycelium that we can see here growing in this tree trunk. Look.
Yeah, it's definitely like a metaphor, right? You can think of a metaphor, like also human could be connected to like technology or computers and see what could come up if this process is ongoing all the time. Like, as I said, evolutionary process, so you never know what the outcome would be, but if you include the input and trace forward to the output, so it's very interesting how it evolves. The signal is not at then just only a random signal, but it evolves in this kind of setup. So that was very interesting for me. Of course, there are different layers packed in behind maybe your project or this setup, like you use antenna, for example, or mushroom as an antenna to generate the sound, let's say. Not to generate, but also generate. It picks up real-time activities, what happened in the mushroom. For this tutorial, I invited Martin Howse to collaboratively work on interspecies collaboration and feedback loops between mycelium networks and their habitats, including living organisms and beings. The tutorial includes 4 experiments presented in my toolkit, mycorrhizal networks, or how I hack plant conversations. The toolkit includes electronic components for building a sensor and a radio transmitter. It also includes coffee grounds in a petri dish, a Arduino microcontroller, plant seeds, and software to bring the tools into action.
Okay, so the experiments introduced in the tutorial will give us an idea of how to grow mycelium, how to make electronic tools and interface with living organisms, and how to use software to connect these tools for audiovisual expression. So we'll be making 4 experiments. The first will involve growing mushroom mycelium on the coffee grounds. The second will be sensing very small changes in voltage within living organisms and mycelium. The third is constructing and testing a simple mycelial transmitter. And the fourth will use supplied PD patches for audiovisual expression.
In this experiment, we will start growing mycelium. The grown mycelium will be used to connect to electronic components in order to sense electric potentials around mycelium network and the habitats. We will use dowels of mycelium and coffee grounds. In case if different amounts are needed, purchase dowels with mycelium at mushroom supplier and collect coffee grounds at home. In this experiment we will use a few dowels with oyster mushroom mycelium, a strainer, coffee grounds, a petri dish, pot and electric stove, and some water.
Put coffee grounds into a pot and pour water on top so it covers them. Sterilize the coffee grounds by cooking them for 10 minutes on a hot plate. Strain the coffee grounds. Leave them for a couple of minutes to cool down. Put the coffee grounds into the petri dish and wait until they reach room temperature. Add dowels with oyster mycelium inside the coffee grounds and cover the petri dish. Place the petri dish in a dark place. Inspect your coffee grounds after a couple of days. In 2 to 3 weeks, you should have your coffee grounds colonized by mycelium. For further experimentation, grow larger amounts of mycelium, plant the seeds provided, and connect the grown plants to electronics. Also experiment with different substrates for growing mycelium, for example, wood chips, cardboard, and so on.
Once the mycelium has reached a level that you're happy with, what we'll start to do is build an electronic interface to bridge the mycelium to the computer and to measure small electrical impulses in the mycelium. So for this experiment, what we'll need is breadboard, AD620 amplifier, 100 microfarad capacitor, 3 1K resistors, Arduino with software, USB cable, jumper cables, electrodes, crocodile clips, and the computer.
Place the operational amplifier provided on the breadboard with its legs bridging the middle gap in the breadboard. Connect the 100 microfarad capacitor between pin 4 and pin 7. The capacitor smooths the power supply from the Arduino. Place the 1 kilo ohm resistor between pin 1 and pin 8. This resistor sets the amplification of the organism's signal to a factor of 50. Add the two other resistors at pin 5 with one ending at pin 7, which is the power, and the other at pin 4, which is the ground. Connect pin 7 to the power source and pin 4 to the ground of the Arduino microcontroller. Connect pin 6 to the analog input A0 of the Arduino. Pins 2 and 3 of the operational amplifier are then connected to the electrode patches, which are then attached to the grown mycelium. Connect pin 5, the reference, to the grown mycelium. The pin sets the ground reference for the amp. Connect the Arduino microcontroller to the computer using the USB cable provided. Open the Arduino application and set the board and the port under Tools in the Preferences. Open the sketch by going to File, then Examples, then Basics, then click Analog Read Serial. In the window, click the right pointing arrow to upload it onto the microcontroller. Go to Tools, open the Arduino serial plotter, set the signal rate to 9600, and see the variation of electric potential in Mycelium in action. For further experimentation, use different mycelium, kinds of plants and/or other organisms, including yourself.
So in this experiment, we'll build a very simple FM or frequency modulation transmitter, which will use the Lindsay mushroom as part of its transmission circuit. And the transmitter will respond very subtly to changes within the mushroom itself, to signals within the space, and to proximity to the human body. And what we're using for the circuit is this logic chip, which we repurpose alongside other components, and the signal can be picked up by any regular FM receiver like this. So for the experiment, what we'll need is the logic chip 74HC04, two 10 picofarad capacitors, one 33 picofarad capacitor, one 100 nanofarad capacitor, a 1K resistor, the printed circuit board, which is here, battery pack, 3 AAA batteries, some lengths of wire, solder, soldering iron, wire clippers, and FM radio.
Orient the printed circuit board according to the diagram. The view is from the top down. You will place parts on the top and solder them from the bottom. Place the operational amp chip provided, the 14-legged item, from the top onto the board. Pin 1, which is just underneath the notch, should be as in the diagram. Turn over and solder each leg in turn. Place and solder the 4 capacitors of differing values and the 1 resistor as indicated. The long leads on the bottom can now be clipped after you have soldered everything. Solder the battery holder with the red lead right, black lead to the left. Solder 1 thick 10 centimeter long bare wire to the frequency antenna spot and one to the transmit antenna spot.
So then, this is everything?
Insert the frequency antenna wire into the mushroom body. Put batteries in and switch on if the battery holder has a switch option. Switch on the radio, place it about 1 meter from the mushroom, and make sure it is set to FM with the switch. Tune the dial until you hear the sound change. For further experimentation, try soldering wires to other nodes on the outside of the circuit board. Insert them into different parts of the mushroom, connect more transmitters to other mushrooms in the same space, take the headphone jack out of the radio, and use it with PD patches or an Arduino sketch.
In this experiment, we will use built tools for setting up feedback loops between electric potentials in mycelial networks and rewired electrical signals in pure data patch. The idea is to influence the growth of mycelia with generated electric signals in response to the sensed electrical signals. Finally, we will use the generated signals for audio-visual expression. For the experiment, we will need the grown mycelium, alligator clips, the built sensor, a USB cable, electrode patches, software, wires, and the computer.
Attach pin number 9 of the Arduino microcontroller to an electrode and place it next to one of the electrode patches of the sensor connected to the mycelium. Attach the ground of the Arduino microcontroller to another electrode patch and place it next to the second electrode patch, connected to the plant in such a way that both electrode patches appear in between the electrode patches of the Arduino microcontroller. Open the sketch by going to Finder, then the USB memory stick provided, and then the Arduino analog to PWM folder. Then open the Arduino analog to PWM file. In the window, click the right pointing arrow to upload it onto the microcontroller. From the Finder window, open the analog to PWM patch with the extended version of Pure Data. Open the active port of the Arduino microcontroller by clicking on the object, Devices. Activate the on-off object of the PD patch so that the patch updates the values captured on the object, turns on the speakers, and activates the window for visuals. If everything is done correctly, the scale of the slider in the patch should start moving left and right, and you should hear sound and see visuals. For further experimentation, add new objects to the PD patch and change the audio-visual performance.
And kind of map those onto human networks or radio networks.
Electromagnetic waves,
Yeah,
basically,
yeah,
in this case.
Yeah, yeah. And to see maybe also like how we can also think about electromagnetic waves in terms of like being parasitic. Like if we have these kind of structures of like mobile phone antennas on buildings, how harmful are those emissions to humans or animals or plants? But at the same time, it can be something which is beneficial. Like we don't need to think of them as parasitic, but as symbiotic, or so this kind of play with like electromagnetics as symbiotic or parasitic, or how much is really how much could be inspired by these kind of networks.
Yeah, I guess. We just call them parasitic or symbiotic.
Sure.
I guess it's just for humans it is maybe parasitic, but it's kind of.
But again, it's like using these things as examples, like how do these mushrooms behave when there are, or the mycelium, how is it behaving when there's not so many resources? How does it kind of share knowledge or pool knowledge? How do humans kind of operate in the same way? So how do human networks spread out? How is information distributed? But also like how it can cross boundaries between species, so it's not just about what is good for one species or another species.
Yeah, so especially in this updated project, Radio Mycelium, what you have right now, so you connect electromagnetic waves from the air, let's say, and connect to mycelial networks. In this case, when mycelial networks are communicating with other species, let's say, or plants, or inside itself, let's say. And of course, electromagnetic waves influences then the activities. And when the output, what you have, radio, so you can turn on the radio and you can hear the influence, basically. With some amplification. Set up a stop as well. Again. And maybe I have to straight